Hey everyone, and welcome to our webinar on Ultrafast Transmission Electron Microscopy Techniques and Applications. I'm Darren Lenhart from Euclid Techlabs, and I'll be emceeing today's webinar. With the growing application of temporally resolved electron microscopy, we created this webinar to provide a solid intro to UTEM and share some of the applications enabled by this powerful technique. Before we get started, we have a few housekeeping points. First, we'd like to get a quick pulse of the audience. So Caitlin, could you please put up our first polling question? You should see a small pop-up window on your screen with the following question: which best describes your UTEM experience, with 4 choices. So go ahead and select the most appropriate answer for the next 15-20 seconds, and then we'll take a look at that. Keep that window open also, please. We'll be using it off and on throughout the webinar. Second point, the webinar is being recorded and will be available next week on the Microscopy Today website. And then finally, our Q&A session will be at the end of the presentation, so feel free to enter your questions into the Q&A tab at the bottom of the screen, but we will get to them at the end of the presentation for continuity. All right, we have the poll results back, and we have a pretty good distribution. Our speakers have their work cut out fairly well for them. This is great. We have a lot of read some papers, but no direct experience as the primary group of our audience, and this is fantastic. This is exactly what we're looking for to accomplish, to get some more users in the community, so to speak. So let's start with our speakers. John was already introduced, but let me try it again. So Dr. John Roehling is from Lawrence Livermore National Lab. He started there as a staff member in 2014, employing TEM techniques to interrogate a broad range of material science issues since his days at UC Davis. His present focus has been on dynamic TEM of additive manufacturing processes, and he will share these details with us today. While we transition to John's presentation, one more poll question for you guys. Caitlin, can you please post question 2? And go ahead, your screen should read: which timescales are best suited for laser UTEM? This timescale is just referring to the temporal resolution of the laser-based technique. We'll give you another few seconds, and then John will take over and give us the full answer to this question. Thanks. John?
Thanks, Darren. As Darren said, my name is John Roehling. I'm a staff scientist at Lawrence Livermore, and I won't read this title again since it's already been read twice, but I'll be talking about the dynamic transmission electron microscope at Livermore and some of its applications. Oh, I need to close this out. Okay, so for this talk, I'm first going to give an overview of what time-resolved transmission electron microscopy is, and mainly talk about differences between dynamic TEM and ultrafast TEM, or DTEM and UTEM as we like to call them. I'll then talk about the development of the DTEM at Lawrence Livermore, both the single shot and movie mode capabilities that we developed and how we got there. And then I'll move into some applications that we have used the DTEM for in the last few years. I won't read each of these individually, let you read those. So DTEM and UTEM are both time-resolved electron microscope techniques. So they're basically high-speed imaging within a TEM column that allows you to look at very fast time scales at very small spatial scales. It's something that's not possible with things like high-speed imaging using optical techniques. So typically, the electrons that you generate are generated through lasers, and as well as the excitation of the sample itself, though not always, as I'll talk about in this presentation, and you'll see a lot more in the next presentation. But the main difference between DTEM and UTEM is DTEM is a single snapshot of a slice of time, whereas UTEM is a stroboscopic method to gather information about a time step after an sample excitation. So because of that, DTEM, because it's a single snapshot in time, DTEM requires a lot of electrons at the same time to be going through the sample. So that necessarily requires a lot of electrons present in the column at one time. And this means you're going to have Coulombic interactions between the electrons, which leads to a blurring effect. And that means DTEM is spatially resolution limited compared to a conventional TEM. So you generally will not expect as high a resolution DTEM as you would in a conventional TEM. The timescales that DTEM is best suited to are microsecond to nanosecond. And this is because you need a little bit longer laser pulse to get the number of electrons that you need into the column compared to something like UTEM. But the advantage to DTEM is that you can look at irreversible processes. So if you have something that goes from state A to state B and then stays there, you can look at how it gets from state A to B without needing it to revert. UTEM, however, needs something that is a reversible process, something that goes from state A to state B and then will slowly relax back to state A. But because UTEM is this stroboscopic process, it doesn't require all the electrons to be in the column at the same time. It can have a single electron going down the column at once. You don't have these Coulombic repulsion interactions between the electrons, and the resolution of the instrument is generally preserved. So it's very similar compared to a conventional TEM. And also because you don't require so many electrons all at once, you can use you can use higher time resolution laser pulses. So your time resolution of a UTEM is greatly increased. It's on the order of picoseconds to femtoseconds compared to DTEM, which is microseconds to nanoseconds. So if we kind of look at the spatial resolution and time resolution space and where they're best suited, DTEM shows is best suited for this boxed area, tens of nanometers to hundreds of microns and tens of nanoseconds to hundreds of microseconds, which is really well suited for things like phase transformations, melting, resolidification, even structural changes in biological samples or nucleation and growth of certain things. My computer seems to have frozen for a moment. UTEM, however, because it has much higher spatial resolution and it's basically operates like a normal TEM, you can go down all the way to sub-nanometer resolutions, all the way up to hundreds of micrometers. And the time scales are very fast, femtoseconds to picoseconds. And because of the way it operates, the beam from a UTEM is much more coherent. So you can look at things like plasmonics, magnetic properties, and even plasmons, or I'm sorry, phonons. So the basics of what a UTEM instrument looks like. So you have a normal TEM column with a port. I don't know if I can have my pointer here, but you have a port that goes into the column that shines on the photocathode, and another port which shines onto the sample. Typically, you have a femtosecond laser where the femtosecond laser has a variable repetition rate as well as a pulse duration, and the energy is typically in the tens of nanojoules per pulse, and that's kind of the higher end. You take this laser beam and you split it into two parts, and you send one part to a second or third harmonic generation. This bumps up the photon energy to a high enough energy where it can cause photo emission from a photocathode. The photocathode is shown up here in picture C. This structure is very similar to what you'd see from a normal TEM tip. It's a very sharp tip, so you get a very coherent beam. The laser spot itself is very small, 20 to 30 microns, and this shines onto this tip. And then if you integrate the having a normal TEM, and the time resolution is very fast. You can get 200 femtosecond pulses out of this instrument. The second half of the laser you then send through a translation stage, and this introduces an extra path length for the laser beam, which introduces a delay, and that's how you set your time delay for your experiment. So you then excite your sample with this lower laser beam, you probe it with your electron, and then the sample returns to its ground state, and you then will repeat that process millions and millions of times while exposing the CCD to capture an image of a single time step. If you want to then do the next time step, you change this translation stage to a different path length and then repeat that process. But you can build up a movie of as many time steps as you want using this. It just generally takes a long time. I will state that one of the limitations of using this setup is that a translation stage is adding path length. So if you want to do long time delays, say in the nanoseconds, light travels about a foot per nanosecond. So a 10 nanosecond delay requires a 10-foot extra path length, which can be challenging physically to just set up if you need to do high precision between femtoseconds all the way to nanoseconds. It's possible, but it's challenging. So DTEM, however, is a little bit different. The pulse duration is a lot longer from the laser beam. It's 5 nanoseconds all the way up to a microsecond. And this is necessary because we need so many electrons in the column at once. So if you have higher intensities, so short pulses, you end up ablating away the cathode material. So you need these longer these longer laser pulses to kind of spread the energy out over time to be able to get all the electrons down the column. But it's a very deep UV, 213 nanometers with about a millijoule total energy in up to 16 pulses. It's typically 9 to 16 pulses. But we shine that onto, instead of a very sharp tipped cathode, a flat tantalum disc cathode, and this is 0.8 millimeters in diameter. The laser spot is 50 to 100 microns. And this means our coherence in our beam is much lower than you get in a UTEM. But you'll see it's still coherent enough to see some things that we want to. You'll see that in a few slides. But the major advantage to our setup is that we have full control over the temporal spacing of our electron pulses. So we can set up the laser beam to photo emit at whatever time spacing between pulses that we want. The other advantage to the DTEM is that because we don't need a laser translation stage to set our time delay, we can excite our sample with a separate laser and timing system, as well as we can use different means other than a laser. We can excite it with electronically or even mechanical means. And you'll see that in some of the applications. So DTEM, the first DTEM was developed at the University of Berlin in the 70s. And Livermore started doing its own development in around 2003. The first instrument in Berlin was a 100 kV instrument, and it used a laser pulse of around 20 nanoseconds, and it was the first demonstration of gathering enough electrons in the column from a single laser pulse to form an image. In 2003, they actually improved it enough to get the first demonstration of a movie mode acquisition. But the resolution of this instrument was relatively low. It was around 200 nanometers, so that's not a whole lot better than optical imaging. So Livermore came in, and we wanted to improve upon that and be able to have a TEM which operates a lot closer to the resolution limit of a TEM. So we introduced a number of improvements. We introduced we had our first demonstration of our single shot mode in 2006, and in 2012 we moved on to movie mode, which had a number of advantages. And the spatial resolution that we improved was about an order of magnitude over the initial instrument at Berlin. So here's some images from the instrument at Berlin. This is of, I believe, of a thin film of metal ablating. But again, the resolution was rather low, and this is because they were using a low accelerating voltage of 100 kV. So there's more time. The electrons are in the column for a longer time, so there's more time for the Coulombic interactions to occur, so you get more blurring. And they also had a little bit lower electrons per pulse than you'd want to get higher resolution, but they did demonstrate this movie mode for the first time. So Livermore's innovation for our single shot mode was to increase the number of electrons that we're getting into down the column onto the cathode. And we also moved from a 100 kV instrument to a 200 kV instrument. So we were able to collect a lot more current and put it down into the sample by introducing the C0 lens, which is basically a very low power lens and a drift section, which allows us to collect a lot more of the photocurrent. And we improved it by about a factor of 20 from the initial DTEM, which a lot of the photocurrent was clipping on these apertures up higher in the column. So just a demonstration of that. Here we have a thermoionic emission, just a normal TEM mode or TEM image of a dislocations and some stacking faults in a metal and a diffraction pattern as well. And you can see a single shot pulsed mode. We still have enough coherence in the beam to see these dislocations and stacking faults and get a nice diffraction pattern with nice tight rings. And with a multi-layer cross-section sample, we were able to demonstrate 9 nanometer resolution. So this was what we were able to do with our single shot mode. We wanted to improve this though, because with single shot, you need a sample, which if you want to get a movie of a particular process, you need a sample which will react the exact same way every single time you hit it, because you need to hit the sample and then move to a different spot, hit the sample, and do this over and over again. So you need a sample that reacts exactly the same, and the laser drive needs to be very repeatable, which typically it's difficult to do that. So what you want is something that can image just a single process multiple times and get that time evolution without needing to move to different parts of the sample. This just opens up a lot more experiments. So we were able to develop that with a movie mode system by redesigning the cathode laser and introducing a high-speed deflector array. And we were able to do this movie mode by introducing this arbitrary wave-generated cathode laser, which gives us the ability to make any pulse train that we want in the UV to basically get us an electron pulse train of whatever duration and spacing that we desire. And this high-speed deflector array will deflect each electron pulse onto a different part of the CCD so they're not overlapping, and then we can easily separate them out into a movie. The cathode laser gives us the capability to do any pulse train that we want, from a 10 nanosecond duration up to a microsecond duration within 100 microsecond, about 120 microsecond window actually. And that's because the way we generate the laser pulses, what we do is we generate a very low energy pulse train of the shape that we desire, and then we amplify it. We put it through a number of amplifiers and we bump it from microjoules all the way up to about a joule. And it's the lifetime of these amplifiers that give us that 120 microsecond window, because they only stay excited for about that long. So any longer and we just can't get the gain in order to change the 1064 nanometer light all the way into 213 nanometer light. But that's the limitation on our important, because the solidification structure.
Hey John, I'm sorry. The slide started, but your audio did not. So would you mind starting this slide over? Because it's really fascinating.
Oh, I'm sorry. Is that, can you hear me now?
Yes, thank you.
Okay. So I was saying we've done a lot of rapid solidification in recent years, and using the DTEM, and this is important because the solidification structure can largely affect material properties. And so here we see the solidification of a thin film of metal, aluminum silicon alloy. And as we move into the melt pool, we can see changes in the solidification mode. Here we have very small nucleated grains moving into larger nucleated grains. And as we move right into the melt pool, we'll see these large nucleated grains transition into a planar growth mode. You can see this, the solidification moving into this kind of line that moves into the melt. The melt is on the right. And then as we move even further into the melt pool, you can see it changes completely to a planar solidification. We've also looked at the change in solidification due to changing the thermal gradient, or if we have a very high thermal gradient, we get this planar growth mode. But if we change the thermal gradient to a much lower thermal gradient, we can get a dendritic growth mode. And as far as I know, these are actually the first images of nano-sized dendrites that have ever been imaged, at least to my knowledge. We've also looked at germanium crystallization and the different growth modes that occur. Here we have an amorphous film of germanium, and we hit it with a laser to heat it up. That causes a nucleation point site to start to crystallize, and then that explosively crystallizes outward. The growth front velocity is about 2 meters per second. And the interesting thing is that as it starts to cool, because the laser spot's a Gaussian beam size, so at the edges it's a little bit cooler. As it cools, it actually changes growth mode. And we thought at first that these growth rings were growing radially, but it turns out that they're actually growing in a spiral. And we were able to see these changes were due to both the thermodynamics and the temperature history, and match that up with some of the models that we developed. We've also looked at nanoparticle reactions. In this case, these are small aggregates of aluminum and copper oxide, or basically a nanothermite. And upon excitation with a laser beam, we start the reaction with a laser, we can see that the changes in morphology. And these changes in morphology, we were able to correlate to and see that they were actually mass or heat transfer limited rather than mass transfer limited. And here's a paper on that, plug for my buddy who did this work. But it was really interesting work on these nanoparticles, and it's some of the higher resolution stuff that we've done with this instrument. We've also looked at reactions of bilayers and nanocalorimetry, and correlated the heat signatures that we see from a calorimeter with the pulse diffraction and the time resolved diffraction of the thin film. So basically correlating the phases that form to the heats of reaction. And this was, excited via electrical pulse, if I remember right. We've also done some high strain rate testing in the TEM. So this is a piezoelectric actuated TEM holder. And these are some thin tensile specimens that were femtosecond machines with an electron transparent region. And we were able to look at the dynamics of fracture at very high strain rates up to 10 to the 4. So here we have some movies of the dynamics of twin formation, as well as the nucleation site of the formation of a crack, how they relate to where twins form. And we are also able to look at the deformation, or the formation of twins, and the deformation of some nearby grains. And lastly, we also have the key, not just to look at thin films and mechanical specimens, but also in situ stages. So here we have an in situ liquid stage. And in this case, we wanted to look at the formation and growth of nano-sized bubbles, which grow and then collapse. And upon collapse, they can cause shock waves that will damage nearby soft materials like polymers or even tissues. So we were able to use the DTEM to image the formation, the growth, and collapse of these nanobubbles, and then correlate it to some of the damage that we saw on nearby witness materials. Compared to a conventional TEM. And this is something that's not possible with optical techniques. Because
Excuse me, John, you blinked out on us one more time. It was right when you transitioned to this slide. So could you restart this slide, please?
Yeah, my apologies.
No problem. Thank you.
Can you hear me now?
Yes.
Okay, I was summarizing. This is a relatively unique capability. It has the ability to characterize irreversible processes with high spatial and temporal resolution that's not possible using optical techniques and high-speed optical imaging, and it fits in a different spatial and temporal resolution regime than UTEM. So we have the capability to look at these irreversible processes with 9 or 16 frames with improved signal from initial iterations. Our time resolutions around 5 nanoseconds up to a microsecond long electron pulses within a 120 microsecond window. And this is much longer time scales than UTEM, but it kind of fits a different window. UTEM is 100 femtoseconds to about 10 picosecond time resolution. And the major advantage, I think, of DTEM is that we can excite the sample through not just laser means, but also through electrical or even mechanical excitation. And so with that, I will end my presentation and let Eric.
All right, thank you very much, John. That was fantastic. The questions are coming in through the Q&A as well as the chat and raise hand. That's fine. We'll take care of all the questions after Eric's presentation. So our second speaker today is Dr. Eric Montgomery from Euclid Techlabs. Eric is the director of R&D at Euclid, joined the team in 2018 from his research scientist and adjunct professor positions at the University of Maryland. Like John, Eric's background is very broad, with particularly deep expertise in novel electron source development. As we transition to Eric's presentation, I have a third poll question for everyone. So Caitlin, could you please set up the third question? Very similar to the last one, which is what are the timescales best suited for RF or laser-free UTEM? And we will give you guys a few seconds to kind of digest and vote on that. And we will turn it over to Eric to hear the answer. Go ahead, Eric.
All right. Thank you, Darren. And thank you, John, for an excellent overview of DTEM and UTEM. In this presentation, I'd like to follow on that with a complementary emphasis, emphasizing the new trend of laser-free UTEM and place that in the larger context of the field. As Darren mentioned, I'm Eric Montgomery, Director of Research at Euclid Techlabs, and we are in the Chicago area, Bolingbrook, Illinois, specializing in linear particle accelerators, ultrafast electron microscopy technologies, and advanced materials. Laser-free UTEM is a relatively new development, so I'd like to start off in this presentation with a historical perspective and comparing the different types of ultrafast instruments. This will be a bit of review from John's talk. Then I'll get to the new part, the laser-free UTEM and how it works, the state of the art, and comparing the various methods that are out there with what I hope is a very fair comparison. We'll conclude with some application and developing trends, and I'd like to put up what I hope are some useful references for our community attending from around the world virtually today. Thank you for your attendance. Historically, in the 60s, we started seeing proposals to do ultrafast TEM, and as early as the late 70s, the first stroboscopic pump probe. Of course, no one would term this ultrafast, and so it was in the early 2000s when the DTEM started its development, and the first 3-frame DTEM was published using flat photo emitters. John detailed the subsequent advances in the DTEM field, of which there have been significant ones in the past decade. As well, UTEM had a parallel development track. Nobel laureate Zawal's group at Caltech was able to show 2 instruments in the mid-2000s and time-resolved spectroscopy. They were also achieving atomic resolution routinely on that second instrument. The development of nano photo emitters, so a technique where the field emission is assisted by the laser photo emission, has been used for high brightness UTEM more recently, and that immediately led to coherent applications where the coherence of the electron beam is absolutely critical, such as electron holography, both with Schottky field emitters and cold FEGs. And lastly, there's been some interesting work in the past few years on not just pump probe, but simply pump, the right kind of pump, time structuring that stroboscopic pulse train to reduce the radiation damage in sensitive biomaterials. So let's have a look at the different ultrafast instruments side by side. Standard TEM, as we well know, is not ultrafast. Its timing is limited by the detector. Even the best detectors cap out at sub-millisecond resolution. The laser UTEM can certainly achieve femtosecond resolution. 50 femtoseconds isn't unheard of for a laser pump, but that pulse is convoluted with the response time of the photocathode, resulting in an electron pulse closer to 200 femtoseconds. or higher. Picoseconds would be typical, and the repetition rate widely tunable. For the dynamic TEM, I won't repeat John, just to say it's a single shot imaging approach, which can be operated in movie mode with much longer pulse durations. And the laser-free UTEM approach inserts an RF pulsar into the column between the gun and the first condenser lens. And this approach I'll detail later, but it can achieve pulse durations from picoseconds on up and repetition rates widely tunable up to gigahertz, even 10 gigahertz. So these various ultrafast instruments result in various modalities. And as John well covered, irreversible material systems result in single shot imaging using many, many electrons per pulse, longer nanosecond pulses typically, single shot per image, and 10 nanometer resolution on up, with microns being very, very achievable. The reversible material systems are well suited for a stroboscopic approach, and their laser-based or laser-free UTEM is appropriate. Also, coherent pump probe is well within reach with the right electron source. And biomaterials, as I mentioned, can see low critical damage from stroboscopic illumination. I'll have a slide on the application of that later. There, you integrate over a large number of shots, just as in the stroboscopic approach, but you try to limit the number of electrons seen by your sample to about 1 million or a bit more. So how does laser-free UTEM work? Maybe this is the first presentation where some of you have seen a UTEM approach without a laser, but the stroboscopic pulsar that we've been working on at Euclid Techlabs is one of a couple of flavors. You can do a radio frequency-based gigahertz pulsar with a resonant deflecting cavity or a traveling wave strip line. So let me show both of those. The resonant deflecting cavity is a fixed frequency RF cavity, typically water-cooled. For compactness, it can be filled with a dielectric. The traveling wave strip line, by contrast, sees 2 RF inputs, one in phase, one out of phase. This results in a well-defined transverse electric field. That field propagates through a slow wave structure, which is phase matched to the electron beam velocity, so that any given electron in the beam sees a virtually constant electrostatic field as it propagates. These two approaches can be contrasted, but they both tend to preserve the original peak brightness of the source, don't require any modification to the gun, and have very similar energy spread to the original source as well. Here is shown a column with the pulsar inserted between the gun and the first condenser. And you can see that the pulsar incorporates in the upper right inset 2 quote unquote kickers. The first kicker, K1, sweeps the beam across the gating aperture, and the second kicker operates to demodulate the transverse momentum of that swept beam. 2 amplifiers are operated with controllable phase and amplitude between them, and a pump probe capability can be included. Here is shown an RF pump where a frequency doubler is required in order to bring the pump rate equal to the probe rate, because the probe sees an electron bunch both on the right to left and the left to right sweep of the chopping aperture. And the operating range is an RF frequency of hundreds of megahertz on up to about 12 gigahertz in its current implementation for the traveling wave strip line. It would be in the mid gigahertz range for a resonant deflecting cavity. The repetition rate widely tunable, and the duty cycle also widely tunable. This technology, not to toot our own horn too loudly, but it was an R&D 100 award winner in 2019 and received the 2020 Microscopy Today Innovation Award. So laser-free UTEM has seen its development over a similarly wide period of time, starting in the SEM community with somewhat smaller ranges of frequencies, and then moving more recently into resonant deflectors in TEM columns at 200 kilovolts, some very nice work coming out of the Netherlands with a 3 gigahertz resonator as well as a dual mode resonator. The dual mode sweeps the beam in a Lissajous pattern across the chopping aperture, and that allows for a lower repetition rate, which can be matched to a very high repetition rate pump laser for pump probe. The traveling wave concept is even more recent, having been developed really in the last 5 years, primarily by Euclid Techlabs and its collaborators. And this technique has been implemented and has begun to see some publications hit the literature. Keep your eyes open. We have several in process. We installed our first instrument with great support from JOL USA in 2018. Our second instrument was installed at Brookhaven National Laboratory on a similar field emission microscope in 2019 at Yimei group, and at NIST in 2020 with Jun Lau's group at 300 kilovolts on a thermionic instrument. So what is the state of the art when it comes to the ultrafast pulsar, the UFP? The resolution, which we're routinely achieving, is excellent. The continuous and pulse beam here at a lower magnification are almost indistinguishable for this Lorentz image of a permalloy square. And this is at 200 kilovolts with a 2.6 gigahertz pulse train for the pulsed beam, which means that the pulse duration is just a few picoseconds. In high resolution, and these images also credit to Spencer Riesbeck and Yimei Zhu's group at Brookhaven, is that in the continuous mode, you can see the lattice fringes, and in the pulsed mode, although you can see that there is a slight difference in the image. However, the atomic resolution is there, and in the Fourier spectrum, the key features are certainly preserved. In diffraction, we can here see for a selected area diffraction image inside the white circle that we get this continuous diffraction image, and then the pulsed image is very, very similar. You can see the outermost ring is maybe slightly less well-defined, but very similar performance. And for coherence, you can see here some Fresnel fringes using a thick moly trioxide sample on a wholly carbon grid. Again, 200 kilovolts, 2.6 gigahertz RF. And we have 4 fringes for the pulsed image compared to 8 fringes on the continuous image. So there is a little bit of degradation of the coherence, but it's still coherent enough. And really what's going on is that as you sweep the RF, it sweeps the beam in one dimension, as shown by the white arrow on the upper right. And the other dimension is essentially unchanged. So you increase your effective source size in one axis, but not the other. And this allows you to get a very coherent beam, especially when you sweep the RF perpendicular to the fringes, which is the key to get images like this. You can also get coherence using off-axis holography. This work done also at Brookhaven by M.G. Han. And the continuous image shows the microscope operating with the RF off, no change. The modulated image shows sweeping that beam, but not aperturing it, not gating that beam at the chopping aperture. So you have the same number of electrons between the continuous and modulated beams, but you can see by sweeping the beam, you do get a much larger background. So then by going to pulsed mode, we are able to get a much cleaner, high contrast image. And I should point out that the number of electrons here have dropped because now we're chopping and throwing away that gated beam. So this is already 22% contrast, and I would expect even better results for equal number of electrons with the continuous and pulsed images compared. So let's try to make a fair comparison of the 4 methods that we've looked at in today's webinar. As we're wrapping up, the laser UTEM, the DTEM, the RF resonator, and the Euclid traveling wave approach with the ultrafast pulsar. You've seen the pulse trains, which can be achieved with these 4 instruments, so I won't repeat that. For the operation mode, single shot, is where the DTEM shines. And movie mode is a beautiful application of that technique. Stroboscopic or single electron regime is achievable with the other three. And then the instrument can be operated in a continuous or native mode by turning off the RF or by turning off the laser and simply running a thermionic beam or a field emission beam. Typically, there is a delay time when switching between continuous and pulsed mode in the laser-based systems because of the need to reset the temperature on the source. So that takes about an hour to switch over, perhaps a bit less. And on the RF side, it's very, very fast, just a few seconds to switch off the RF. The sample excitation for pump probe experiments is widely possible across all four instruments. And the pump repetition rate, as you know, is ideally equal to the probe repetition rate. So where you run into trouble is you cannot probe faster than you pump. And that means with the RF resonator and its very, very high repetition rate and lack of tunability, it's not compatible with the slower repetition rate electrical or mechanical pump methods. But with the UFP and a pulse picker, we can achieve very low repetition rates. And with the laser-based systems, it's also possible to synchronize a laser pump with a laser probe, or even an RF pump with a laser probe, because it's okay to pump faster than you probe. It all depends on the response time and recovery time of your irreversible system, of your reversible system. In terms of performance, the laser UTEM can certainly achieve the atomic resolution and sub-EV energy spread and coherence if you use the very best nanophoto emitters. A typical flat photo emitter won't quite be able to achieve that level of performance. So select instruments can certainly achieve excellent, excellent performance in laser UTEM. And in the RF resonator world, very similar as well, although I haven't seen atomic resolution in the literature, it very well should be possible, as well as with the UFP. Tunability is smoothly variable in terms of beam energy. So you could change from 200 kilovolts to say 100 or 80 kilovolts on your instrument, unless you're doing the UFP, because that requires a phase match in between the electron velocity and the propagation of the traveling wave. Smoothly variable rep rate is possible for all but the RF resonator approach. And availability is improving. So we're starting to see commercially available products over the past several years, both in the laser UTEM world and now with the UFP. The add-on cost of a UFP is less than $1 million for someone who has an existing TEM instrument. Developing trends in the field are really exciting. So I think there's a lot of room for new ideas and some very, very good work to be done going forward. The stroboscopic pump probe with picosecond or even femtosecond resolution starts to allow things like studying of spintronics, plasmon resonances, magnetic materials, skyrmion transport, magnon excitation and magnetic vortices, dynamic imaging of MEMS and NEMS systems, and then the study of phonon dynamics, as John mentioned, as well as reversible phase transitions. Stroboscopic low dose is an exciting area as well, and I'll show in the next slide, the application slide, that you can get 2 times more signal for the same critical dose, or you can double your critical dose, is another way of putting it. And the longitudinal beam bunching is another area developing. It's already common in ultrafast electron diffraction on large particle accelerator facilities, but you can do cavity-based, RF cavity-based compression to achieve higher temporal resolution, shorter pulses than are coming from the gun at the cost of wider energy spread. And then the coherent techniques, I can't go by those without mentioning time-resolved electron holography, which is being pursued by several groups, as well as coherent manipulation of the beam quantum state, which is an exciting new area, for instance, via electron-photon interactions in the column, which could in turn give us attosecond pulse trains. Having said all of that, I do want to show an application slide. So here's an example of mitigating radiation damage in biomaterials. Compare the slope of the red and blue curves, and you can see that the diffraction pattern for both paraffin and purple membrane fades quite a bit slower using pulsed beam in red than continuous beam in blue. This means you can put more electrons on your sample before they're damaged and get more signal as a result. I want to acknowledge funding from the NIH and DOE Basic Energy Sciences for a lot of this work, specifically with the UFP and also with the NIST contract, and our collaborators along the way at Brookhaven, NIST, Lawrence Livermore, and Joel. And of course, the mention of any of them is not to imply an endorsement of any commercial product. Selected reviews for our audience. I've found just a few. This isn't intended to be a comprehensive list, but 3 very good reviews of the field. And I'll leave up some references on the laser-free UTEM approach as we transition to questions. Thank you.
All right, thanks, Eric. That was really excellent also. Ready to open up the Q&A. We have quite a few questions and answers. I'm going to go ahead and put in our email contact information for us into the chat. If anybody wants to reach out to us later, you're more than welcome to follow up some questions. And I'll start off with one of the first questions we received from Luca. He's asking, in UEM, with 1 or few electrons per pulse, acquisition times may be very long, minutes per image for diffraction pattern. What are the requirements for detectors? Would a hybrid pixel direct electron detector like Dectris, for example, be beneficial? I think that one's to you, John, if you don't mind.
I'm actually not sure if I quite understand the question, to be honest. I thought that was more along the lines of a stroboscopic question.
Sure, I'll take that one.
All right.
So in stroboscopic UTEM, very long integration times have been typical for the laser-based instruments, a few minutes or even hours to achieve series of images. This involves very stringent requirements on instrument stability, of course. So you can get a gain from using an electron detector with higher quantum efficiency, so you're not throwing away electrons, but there's a limit there. I mean, 100% quantum efficiency is the best we can do with a detector. I would perhaps mention that what's more important and offers more opportunity for rapid acquisition is a high repetition rate in a stroboscopic system. So as long as your sample can recover quickly, you actually want to send those single electrons to the sample as quickly as it will tolerate and then reset. And those high repetition rate systems are really where the laser-free approach shines, and you can achieve gigahertz repetition rates and acquisition times in seconds with a stroboscopic mode instead of minutes. Thanks, Darren.
Hey, no, thank you, Eric. Great answer. Tal asked 2 questions. I think they're kind of related. One is, what limits the pulse duration in UTEM? That's question number 1. And the second question was, why can't you use 2 different lasers for UTEM, which I presume one laser for the photocathode, the other laser to pump the sample. So, gentlemen.
I think Eric would be better suited for the first question.
All right.
As far as the second question, why it's difficult to use 2 different lasers for pump probe and UTEM. From what I understand, it's very difficult to get that sort of speed in electronic timing. When you're talking picoseconds or femtoseconds, it's just very difficult to get that level of accuracy in the timing, where it's easier just to set up a translation stage to just delay your laser beam by a path length. I mean, if you're talking femtosecond time delays, it's about a micron of distance per femtosecond. It's a very short distances.
Okay. And Eric, how about the pulse durations?
Sure. So I assume our question refers to what is the shortest pulse duration you can achieve. And that at the present time would be with the laser-based UTEM using a very small emitter tip and using a very, very short femtosecond laser. The shortest I've seen in the literature, and I've certainly not performed a comprehensive survey, is, as I mentioned during the talk, a 50 femtosecond laser pumping a photoemitter with resulting 200 femtosecond electron pulse.
All right.
It could be possible to go a bit shorter than that, but that's roughly the current state of the art.
All right. Thank you, Eric. Let's take a final poll question that we have for the audience this time. So Caitlin, could you please put up question number 4? And the question should read, besides probing of samples on ultrafast timescales, UTEM techniques can be used for, and we'll let the audience take a moment to answer those questions with the 4 choices. I also like to mention there's a brief survey at the end of the webinar, which we would really appreciate if the participants could complete. I believe it'll automatically come up when the webinar ends, and you could individually answer those questions. Okay, we're looking pretty good here. I'm gonna end polling and share this time. I think I figured this out. Share results, and yeah, we kind of wanted this the audience to see all the above. A lot of fascinating new techniques and applications are coming out, which has been some of the sources to some of the coming up questions. This is a good lead-in. There's a lot of new applications coming out allowing the UTEM technique to come up. So from Karen, she's asked a question, the beam damage that is slower is interesting. I think she's referring to one of your last slides, Eric. Is there any understanding or details of the last slide?
Very good question. And I alluded to some papers in preparation. One of those is that, however, I think it's early in the game yet to assign a specific physical mechanism or mechanisms to the reduced beam damage. At present, all we can say is on several different types of instruments, both laser-based and laser-free UTEM, we continue to see this effect. It's real. And the slower damage with a pulsed beam covers a wide range of timescales, picosecond to nanosecond, or even above.
Excellent. Thanks, Eric. Bernd, there's the presentation. He's asking for references. The presentation will be available next week, and you could download or copy those references directly yourself in just a few days. So we won't take a moment for that. Another question, I think this came during John's talk. How could you make sure the temperature of the sample experiences, I think it should read, how could you make sure that of the temperature of the sample inside of the TEM? I think this is during the laser. Yeah.
Measuring the temperature inside the TEM is a very challenging thing. It's something we have actually not been able to do as of yet. If we want to know what the temperature is, we typically model it. So we know we measure the laser energy, we know the absorption, and we can kind of model the heat transfer. That's how we typically do it for thin films. But yeah, it's a difficult problem, and it's something that's kind of on our wish list of being able to do.
All right, excellent. A question, I think this is for Eric from Jiayang. How to achieve the large tunable range in frequency of the RF approach?
Sure. So the high end of that range, the megahertz to gigahertz range, is achieved simply by tuning the RF frequency, which propagates through the traveling wave structure. The low end of that frequency range is performed by using a pulse picker. So we start with a stroboscopic pulse train at high repetition rate, and then we use a fast electrostatic deflector to pull individual pulses out of that at the preferred repetition rate.
All right, thank you, Eric. Following up on the radiation damage slide, is the reduction in radiation damage observed at room temperature also observed at cryogenic temperatures? I don't know the answer to that one, but I'm sure Eric has something for us.
Excellent question. That's something we are very curious about. And as far as I know, it has not yet been published. So I'm going to hold off on giving a solid answer on that, just to say people are looking at it.
Okay, fair enough. Work in progress. From Bernd, is there any chance of time-resolved nanocalorimetry in the TEM? I think this is going back to John's recent answer. There were some indications towards this direction in the first talk. So yes, again, this is at you, John.
Yeah, I think that all depends on the time resolution that you're really interested in. I didn't allude to it too much because it makes it look a little bit less interesting. But the time resolution on that particular experiment was, we were doing heating rates of about 1,000 C per second. So we weren't in like the nanosecond regime for time resolution of the nanocalorimetry, but we were in the millisecond regime in terms of looking at the heat signatures versus the phases that form. So
okay,
depending
great.
on what you're really interested in.
Okay. Yeah, so John, you probably weren't aware of it, but you blanked out early on in the presentation. There's been a couple of questions about what did John say. We really can't go back and recover that, but I think we've been answering enough questions that we hopefully covered what may have been missed in that one slide before we realized the problem. From Richard, do the advances in DTEM/UTEM enable elemental mapping eels at similar temporal resolutions?
Yeah, eels mapping, at least in DTEM, is very challenging because you're cutting out, you already are signal limited, but when you're using eels, you're even more signal limited because the inelastic electrons are even fewer than your elastic electrons, and then you are also just interested in only a portion of those inelastic electrons. So it's a very challenging problem in at least single shot DTEM. With UTEM, it's a lot more of a possibility because you can integrate over as long of a time as you want. It's there's been some work looking at low energy excitations in plasmonics using laser-based UTEM. There was I believe it was a science paper a few years ago.
Okay.
I would concur with John on that, and also say that it depends on the specifics of your beam and your source, of course. So with a very high bunch charge, the Coulomb interactions are going to result in some energy spread, and that will limit what you can do with eels. And in fact, even the excess photon energy from some photoemitters can result in a larger energy spread than you would prefer to have on the millielectron volt, hundreds of millielectron volt level. The excess photon energy can be up to a significant fraction of an electron volt. And I would also say that the specifics of how you bias, for instance, the Vaynelt and what you illuminate in laser-based UTEM matters quite a bit for how the eventual energy spread turns out for applications like eels.
Thanks, Eric. Some RF questions now. So this is going to go to you, Eric. Do I have to be an RF engineer to employ these RF techniques?
Fair question. The goal in any product is to make it turnkey, computer controlled, something that could be remotely walked through via a training session as needed. And we're certainly seeing that capability with the laser-free UTEM in our installations right now.
Okay. We're able to go till 5 past the hour, so we're going to continue since we have about 4 or 5 more questions. We're just going to continue just for a few more minutes. Another RF question in RF UTEM is the synchronization between the laser pulse and electron pulse okay? I guess we're talking about mixing the two pump probe techniques.
Right. So can you pump with a laser and then probe with a laser-free UTEM? That has not been published yet, but in principle, it can be done. And the reason I'm confident is because in the particle accelerator community, it's very, very typical to synchronize a pump laser to produce a photo-emitted electron beam with RF cavities for acceleration of that beam downstream. And so the synchronization of lasers and RF elements to the sub-picosecond level is standard technology, virtually off the shelf. So it can be done, but it has yet to be demonstrated in the literature.
Question about the webcast from somebody who unfortunately had started a little late. Yes, this webcast or this webinar will be reposted on the Microscopy Today website probably early next week when it's available. So you could review it and come back to see the references and the speakers and all that good stuff, all their presentations. One more question I have got to admit, I'm not sure I understand it. And if you guys understand it, then we'll pass on it. Can we use fluorescence tagged antibodies to see specific epitope? Does that make sense to you guys? Out of my regime for sure.
Might be a typo. I think the question pertains more to optical microscopy because fluorescence is something you would do there.
Okay, fair enough. What limits the coherence and what methods would you suggest to improve the coherence in a UTEM mode?
Well, source size plays a big role. And it's also interesting that you can trade off the two transverse dimensions of the beam. So if you start with a given beam and then you make it more elliptical, you can gain in one dimension what you give up in the other. And for holography, that's sometimes beneficial. So using an elliptical beam is an option. Getting smaller source sizes is definitely key. The brightest sources, of course, are those nano photo emitters, or using a field emitter, which is gated by a laser-free approach.
Okay, thanks, Eric. This is probably our last question for the session. I kind of like it. Hopefully we could give some insights here. How many UEM and DTEM are currently working worldwide? Any best guesses? Well, let's start with DTEM. Let's put John on the spot. He had a little break there.
I only know of a handful. I can think of, I think 4 or 5 off the top of my head. I've only seen published results from 2 or 3 of those instruments.
Okay.
How
about UEM overall worldwide? What would you guys say?
Right. As of 3 years ago or so, we were at about a dozen. That number has surely gone up. I think some of our attendees may actually know the count better than I do at this point, but I would venture to guess 20 or more.
We should have made that a polling question. I wasn't prepared. I'm sorry. Excellent. Okay. Thank you, gentlemen. I think we're pretty much wrapped up on our time. I have just a few seconds before 1:05 on my East Coast time. So thank you, John. Thank you, Eric, very much. Thanks to the attendees. Please stay on to finish the webinar questionnaire that's going to be showing up shortly. And everybody have a terrific day. Thank you all very much for attending.